Inside the suffocating heat beneath factory floors and steamboat decks, a single crack could turn routine into mass death. Steam boilers held water so pressurized that a sudden breach unleashed a blast more violent than artillery, expanding 1,700 times in an instant. For 19th-century boiler operators, every shift was a gamble with invisible energy they could barely understand, and survival came down to chance. The true reason their job was so deadly is not what you have been told. The physics behind it will change how you see every explosion that followed. Inside every boiler, the true threat was never the fire itself. It was the hidden energy packed into liquid water, forced far beyond its natural limits. At atmospheric pressure, water boils at 100 degrees Celsius, but inside a 19th century boiler, pressure could climb to 100, 150, even 200 pounds per square inch. Under those conditions, water stayed liquid at temperatures well above boiling, quietly storing energy like a loaded spring. 1 liter of water, superheated and trapped under pressure, will suddenly expand to 1,600 or even 1,700 liters of steam the instant that pressure is released. This is not a gradual process. It happens in milliseconds. A single rupture or failed seam, and that invisible reserve flashes to steam, unleashing a force powerful enough to hurl iron plates hundreds of meters and turn factory floors into rubble. This is the physics that made every boiler a potential bomb. The relationship between pressure and volume is not just theoretical, it is a brutal fact. A pressure-volume diagram of water under these conditions shows a steep, sudden leap. As soon as the pressure drops, the volume rockets upward. The human eye never sees the transformation. Operators might hear a hiss, but by then the expansion wave is already tearing metal apart. For every operator working in the heat below decks or behind factory walls, the numbers were not abstract. They were the difference between routine and disaster, measured in fractions of a second and thousands of liters of expanding steam. Boiler operators worked in spaces that barely felt human. Deep below the factory floor or tucked under the decks of riverboats, the boiler room was a world apart, stifling, dim, and always loud. Coal dust hung in the air, clinging to skin slick with sweat. The heat pressed in from every side, radiating off brick walls and the iron belly of the boiler itself. Breathing was heavy work. In summer, the air barely moved. In winter, the cold outside never reached this far down. These hidden, brutal spaces wore operators down, day after day. Operators learned to read the room by instinct. Gauges were unreliable, so they listened for the hiss of steam, the groan of metal, the steady rhythm of the fire. Routine was survival. Shovel coal, check the water glass, tap the gauge, watch the fire's color. Each task had its rhythm, repeated hour after hour. Even the smallest change, a new creak or a sudden silence, set nerves on edge. Most never saw daylight during a shift. Meals were quick, eaten standing, hands still black with soot. Sleep came in short bursts, ears tuned for alarms that might never sound in time. The daily ritual became the only sure guide. Every operator knew the danger was close. They worked just feet from the boiler's shell, separated from disaster by nothing but iron, rivets, and habit. There was no warning for the moment things went wrong. A life spent tending the fire could end in a single breath, with no chance to run. In these rooms, routine was both shield and trap, offering the comfort of habit right up until the instant it failed. A single decision could tip the balance from routine to catastrophe. It often began with something as simple as a slightly low water level in the gauge glass, easy to miss in the haze and heat. The operator, pressed by the demands of production or the push of a river current, shoveled coal harder and fed the fire. The boiler plates glowed hotter, but the water inside did not rise fast enough to cover exposed metal. A valve, stiff from years of mineral buildup, refused to budge when checked. The pressure gauge, lagging behind real conditions, still read within the safe zone. But inside, The story was changing by the minute. As the fire raged, steam formed faster than it could escape. The pressure inched upward, but the gauge needle barely moved because its mechanism was sticky from age and grime. The operator, trusting the instrument, kept firing. An unexpected draft swept through as a door opened above, feeding the flames and pushing the temperature even higher. The water, now dangerously low, left parts of the boiler shell exposed to direct heat. Metal began to blister, unseen. Suddenly, the load shifted. A machine on the line shut off, or a paddle wheel eased for a bend in the river. Demand for steam dropped, but the fire did not. Pressure spiked in seconds. The relief valve, meant to be the last defense, was stuck or weighted down to prevent steam loss. In that instant, the margin for error vanished. The operator, watching dials that lied, had no warning. The chain reaction was complete. Overheated metal, hidden pressure, no escape route. Disaster struck in the space between one heartbeat and the next. Pressure inside a boiler could race from manageable to murderous in seconds, triggered by jolts no operator could predict or control. A sudden change in steam demand, a machine shutting down, a paddle wheel easing off for a river bend, meant the system no longer drew off steam at the same rate. The fire, still raging under the shell, kept feeding energy in, but nowhere for it to go. In that instant, the pressure did not just rise, it spiked. Early 20th century tests, built to mimic these 19th century disasters, showed pressure could leap from safe to rupture in under a minute, sometimes in half that time. Environmental surprises made things worse. A gust of wind down the chimney, a door thrown open, or a shift in outside weather could change the draft in a heartbeat. More air meant hotter fires, and hotter fires meant more steam, whether or not the machinery needed it. Operators, buried below decks or behind brick walls, could not see these changes coming. They might feel the temperature climb or hear the fire roar louder, but by then, the pressure wave was already building. There was no buffer, no real warning. The gauges lagged behind reality. The sound of the fire masked the hiss of rising steam. When the load shifted or the draft swung, the boiler's internal balance tipped from routine to red alert in moments. By the time an operator sensed something was wrong, the margin for action was gone. The system was locked on a course to failure, and the next link in the chain was always the shell itself. Iron plates inside a 19th century boiler rarely failed without warning, but the warning signs were invisible to the naked eye. Deep within the metal, tiny flaws, slag inclusions left over from imperfect smelting, and microscopic voids in the iron waited for years under relentless pressure. Each time the boiler was fired and then allowed to cool, the metal flexed and contracted, concentrating stress at every rivet hole and seam. Over time, those weak points grew brittle. When pressure spiked, the weakest spot gave way first. A crack would shoot outward from a rivet or along a seam, often following a line of slag or a thin patch in the plate. Hoop stress, the force trying to burst the cylinder apart, was twice as high as the force running lengthwise, so cracks raced around the barrel like lightning. In less than a blink, a hairline fracture could rip open the shell, peeling back iron in jagged, torn sheets and unleashing the full fury trapped inside. The blast tore through everything in its path. In factories, the iron shell split open with a sound like thunder, sending a shockwave that heaved the floorboards and buckled brick walls. Heavy machinery was flung aside, timbers snapped, and glass shattered in a rain of shards. Workers on the floors above felt the ground lift beneath them before the ceiling gave way. On riverboats, the force ripped through wooden decks, hurling red-hot fragments and scalding steam across crowded cabins. Deck planking splintered into jagged missiles, and the hull split wide, spilling boilers and cargo into the river. Operators, standing just feet from the point of rupture, were struck down instantly, caught in the first rush of steam and flying metal, with no chance to escape. Survivors described the aftermath as bodies thrown clear, smoke and steam choking the air, and silence falling as the blast wave faded. In a matter of seconds, routine had turned to ruin, and the hidden power of steam had claimed another set of lives. Steam still powers cities and industries worldwide, now under higher pressures than ever. Every safety code is written in the aftermath of tragedy. The lesson endures. Invisible risks demand relentless vigilance, because progress without precaution always puts lives on the line. What safeguards would you demand today?